Okay, moving on. We are now in the second part of chapter 3, and we've learned about moles. So now we're going to talk about well, at least with elements, so we're talking about moles with compounds. So, first thing is to calculate the molecular mass, molecular weight of a compound. And the way you do it is you just take the number of the atoms of the first element times the atomic mass of the element and do that for each subsequent element. So let's start out by doing it for glucose. And one thing to note, these subscripts, so C6, that means there's 6 carbons, H12, that means there's 12 hydrogens, and O6, that means there's 6 oxygens. So the way that you would calculate this out is you would look at carbon, so that's 6 times the molecular weight of carbon, atomic mass of carbon, 12.01, and I'm getting that number from the periodic table right there. So right there, plus 12 times that for hydrogen, 1.008, plus 6 times 16 for oxygen. And if you do that, you find out it's 180. So I have it memorized as 180.16 AMU, or atomic mass units, or you could also write it as grams per mole, usually more frequently grams per mole. So that means that if you have 180.16 grams of glucose, you have 1 mole of glucose. Okay, so just like we saw with elements, we can do this with molecules as well. So what about acetylsalicylic acid? So that's aspirin. So an aspirin tablet, it has other stuff in it. It has binder and starch and that kind of thing. But if you have a 325 milligram tablet of aspirin, how many acetylsalicylic acid molecules is this? So first thing, calculate the molecular weight. So it's going to be 9 times 12.01 for carbon, plus 8 times 1.008 for hydrogen, plus 4 times 16 for oxygen. I know it's 16.00. And if you do this, you get 180.15 grams of aspirin per mole. I'm going to say A for aspirin. Okay, so let's do molecules. So dimensional analysis, 325 milligrams aspirin. So then we have a gram to 1,000. I guess it should be aspirin. I'll do it properly. Gram to 1,000 milligrams. That's just to convert to grams. Then we have a mole of aspirin to 180.15 grams of aspirin listed there. That's an ugly line. I'll do a straighter line. There we go. And then we have 6.02 times 10 to the 23rd aspirin molecules, 2 mole aspirin, like that. And units cancel, milligrams cancel, grams cancel, moles cancel, and we're left with the aspirin molecules, and that would be 1.09 times 10 to the 21 aspirin molecules. Okay, so now I wanted to see how you can do. So if you are following, turn off your, go ahead and turn off your, or put it in pause and try this one out. Carbon 13. So I'll give you a hint in a second. So go ahead and try this and pause. Need a hint? Calculate the molecular mass as 13 times 12.01 plus 18 times 1.008 plus 2 times 16. And the way you set this up, 200 milligrams gram, 1,000 milligrams. So then mole IV2 so that's the way you solve that one. And I am not going to do a calculation because I know the answer already looking at it. So the only answer that makes sense is B. So when you are looking at a test and you're looking at an answer, a lot of questions are multiple choice. So I do that in my class. And if you're going to go on and do pre-professional tests, take the GRE, the GMAT, the MCATs, these kind of things. If you or LSAT, maybe you want to be a lawyer, right? So there's lots of tests and they're multiple choice. You need a strategy when you do it. And one of the easiest ways is to start eliminating answers. So how many ibuprofen molecules are in a 200 milligram tablet? So looking at this, D is wrong because you can't have less than a molecule, right? So a molecule is a whole number and you cannot have a fraction of a molecule. So D is wrong. C is also out. That's too small, right? You looked at the previous example of aspirin. You're looking at 10 of the 21 molecules. So now you have to choose between A and B. And A means you're going to have a full mole of something. And just looking at the ibuprofen molecule, that's going to be something on the order of at least 200 grams per mole. When you don't have 200 grams per mole, you have 200 you don't have 200 grams of it, you have 200 milligrams. So it's got to be B based off of order operations. But you can go ahead and do the whole thing. Now let's see if you can try to figure this out. How many atoms are in that 200 milligram ibuprofen tablet? Not just the other stuff, just the ibuprofen. So hint, ibuprofen has 33 atoms. The 13 plus 18 plus 2, so 13 carbons, 18 hydrogens, 2 oxygens, that's 33 atoms. Okay, so the only answer that makes sense, again, is C, right? Because it's not a mole, we know that. It's 33 is too small, and A is the same. That's how many molecules you have, so it's just that times 33, so which is going to be C. So, okay, so when you do some of these, try and see what makes sense, and you can logic your way through things with very quickly. Okay, so moving on, let's look to see what's other stuff. So, if you look here, and you have the mass of chlorine in Freon 112, a CFC refrigerant. A CFC, so a CFC means chlorofluorocarbon. So a celebrity Jeopardy question, what types of atoms are in chlorofluorocarbons? They're only chlorine, fluorine carbons. So that's one thing with some of these names, they mean something. So a CFC, chlorofluorocarbon, means something. It means that this has chlorine, fluorine, and carbon in that. So what's the mass percent of chlorine? So there, you might say, where's the equation for this? Many of these are considered common sense. So think of body fat percentage, right? So if you're 20% body fat, that means that for whatever percent of weight you are, 20% of that is fat. So if you are a 100-pound person and you have 20% body fat, that means you have 20 pounds of fat in your 100-pound body. So how do you figure out the mass percent here for chlorine? You need to figure out the mass of chlorine over the total mass. And then you multiply it by 100% for that. Okay, so the mass of chlorine, there's 4 chlorines, so 4 times the mass of chlorine, 35.45, and that's the molecular weight of or atomic mass of chlorine. Then this is over the whole molecule, 2 times 12.01 for carbon plus 4 times 35.45 for chlorine plus 2 times 19 for the fluorine. And if you do that, you find out, times, I should put the molecule in, then times 100%. And if you do that, you get 69.58% chlorine. Okay, so, and then that's the percent mass of chlorine. So recap, looking at the percent mass of something, look at the mass of whatever it is or the total mass. And in this case, so we look at the molecule itself and we look at how much chlorine is in there. We divide it by the total mass of the molecule and we find out that it's about 70% chlorine. Okay, next one is chemical formulas as conversion factors. So hydrogen might replace gasoline as a fuel. Most major automotive companies are developing vehicles that run on hydrogen. The cars that are environmentally friendly because their only emission is water vapor. One way to do this is to crack water to form hydrogen. What is the mass in hydrogen from 1 gallon of water? Okay, so we have to go through and calculate this one out. So again, it's dimensional analysis. We start out with so we're going to start off with 1 gallon of water, and we're going to work our way towards grams of hydrogen. So gallon, we need to convert that to liters. So that's, metric unit, and then the density of water is 1 gram per milliliter. So a gallon of water to liters, then convert that to milliliters to grams, and then we got to get the percent hydrogen from the water, and then I guess you don't need the percent, you can just calculate directly from the moles, and then get the mass from that. Okay, so let me show you. So you start off at the left, 1 gallon of water, and I 3.78, I think, yeah, 3.785 liters per gallon. I know liters water, gallon water. And then we have 1,000 milliliters per liter. And then we have a gram water per milliliter. I'll put the water here just so you. So be exact. And then there is a mole of water for every 18 grams of water, and because that's the molecular mass of water. And then we have 2 moles hydrogen per mole water, and then we have 1.008 grams hydrogen per mole hydrogen. And you can see here everything cancels. Gallons cancels, liters cancels, milliliters cancel, grams of water cancel, moles of water, moles of hydrogen. So now it is 3.78 times 1,000 times 1 divided by 18. Oh, 10 times, I forgot the 2 on the top. Times 2. Oop, I read it. Blue. And if you do this, you get 423 grams of hydrogen. And This doesn't seem like very much. So if you look there, a gallon of water weighs, I think, around the order of 6 pounds. It's pretty heavy. You know, it says 3.78 kilograms. That's going to be more like 8 pounds. Okay, that's like 8 pounds. So a gallon of water weighs 8 pounds, and you're getting less than a pound, about a pound of water from that. Like, what's going on? Don't forget though, water is only about 1/9 hydrogen. So we're actually we tend not to crack water. So when we get hydrogen, we don't really get it from water. We get it from what's called steam reformation. So we take usually methane plus water, and depending on how we tweak the process, we either get CO2 and H2 out of it. You can also get CO plus H2. Depends on how you tweak the process, but I know I haven't balanced this either. I know that it just depends on the process. You get different ratios of things, but that's typically how we get hydrogen. The other way you can get hydrogen is what's called molecule reforming. That when in distillation columns, you can reform molecules, you can cyclize them, and that produces hydrogen. So that's more of a waste stream of hydrogen than an actual uh, volunteering what you want that hydrogen. Cracking water, the only time that we really use this is in nuclear submarines. And they crack the water to breathe the oxygen, and they dump the hydrogen. So it's the other way around. This is, but then again, you have to crack the water to get the oxygen to breathe in a nuclear submarine because there's plenty of electricity and but we tend not to crack water to get hydrogen for anything usable. We tend to use steam reformation, for instance. So it's a good idea. You know, it'd be nice because that's one way you could take. Because wind power is not very useful. Unfortunately, it's just not very useful in a grid at all because it surges and it stops. So it might be a good use for wind power. But okay, but recap with this one, it's still dimensional analysis. And you can see as long as you keep your units straight, you can go for the right answer. Okay, obtaining empirical formula from experimental data. So this is kind of old school chemistry, like a while at once. So like after the alchemists, there was this period of just chemistry. This, what's in this? What's this stuff made of? And so we did a lot of effort to figure out what things are made of, and various ways were done. We're not going to talk about combustion analysis. That's the same thing. We would burn a lot of things to see what came off, but we would go and figure this out. So, but let's do this. Let's see what's in this stuff. A compound containing nitrogen and oxygen was decomposed, found to have 24.5 grams of nitrogen and 70 grams of oxygen. What is the empirical formula? So chemistry, your reflex should be moles. So I'm trying to train you to think, okay, moles, moles, moles. So we have 24.5 grams of nitrogen times moles nitrogen to 14 grams of nitrogen. Likewise, we have 70 grams of oxygen to moles oxygen to 16 grams of oxygen. So in doing that, what we find out is we have 1.75 moles of nitrogen, and we have 4.38. Wait a second. 4.38 moles of oxygen. And you're like, okay, I'm done. So we have nitrogen 1.75 and oxygen 4.38. And I'm done. No, you're not done. Because atoms have to be whole numbers. So when you dealing with atoms, you have to do a process called discrete mathematics, and where everything has to be a whole number. So what you do is you divide both sides by 1.75, and in doing so over here you get a ratio of 1 to 2.5. Okay, so now you're like, okay, good, I'm at nitrogen 1, oxygen 2.5. That is also wrong. You can't do that because you're still at 2.5. So what do? You multiply it by 2, and now you get a ratio of N2O5. And that is the right answer. So you can stop there. You have the empirical formula there. Now, okay, so let's recap here. So we have 24.5 grams of nitrogen, 70 grams of oxygen in this molecule. And so what do? We convert the grams to moles. Then we divide by the lowest number to get the ratio of 1 to 2.5. We have to multiply by 2 to get the whole number ratios. And the next question I get from students is, what number do I multiply? Well, you do it by the fractions. If it's 0.5, you multiply it by a half. If it's 0.33, you multiply it by 3. If it's 0.25, you multiply it by 4. And if it's 0.2, you multiply it by 5. And that's because of the fractions. So, like so. Now, your turn. Ibuprofen is 75.69% carbon, 8.8% hydrogen, 15.51% oxygen. What is the empirical formula? So I'm going to leave this up to you, and the answer, of course, is previous in the lecture when I talk about ibuprofen in the chem quiz. So you should already know the answer, but why don't you try that out? And if you get stuck, feel free to ask me for assistance. And I will see you for now.